So yes, I will talk about the basics of parallel programming and and also uh, about some tools, yes, to monitor the resources. So Brigitte has mentioned the terms serial, parallel, right? And I will explain here what is this. So a parallel program, right? It's a parallel program is writing a code, yes, that can execute a task on different computed units. And the key term is that this is done simultaneously. Yeah. So previously in a computer, there was only a central processing unit called CPU also. And therefore, the programs were executed serially. And this is what Brigitte mentioned previously for a single serial program. But currently, the computers contain several CPUs, right? And also there are cores inside the CPUs, which makes the architectures more complicated, more elaborated. For instance, here in a laptop that I am using currently, I can see that it contains several cores, right? And here we can start doing some parallelization. However, if you want to scale your program, yes, beyond this number of cores in your laptop or your PC, then you will need something like our clusters, right? I will talk about two different types of programmings, and they are called architectures, as also in computing science. And here, one talks about the shared memory and distributed memory. Here, the main point here in shared programming is that the cores can share the memory, as the name suggests, right? And why this is useful? This is because the cores can get access to the same memory space, and usually this results in a very fast programming mode. Yeah. So the cores can take advantage of this high bandwidth. Yeah? However, these type of architectures, right, are limited by the number of cores that can share some memory. For instance, at HPC2N, we have some nodes that contains cores, 128 cores that can share some memory. But beyond this number, if we want to scale our code beyond this number of cores, then we need something extra. Yeah. And this is provided by the distributed memory, where the cores can share some local memory, as in this case here, but also instead of sharing the memory directly, they can use some protocol to exchange messages and exchange data among them, yeah. And this allows you to scale your code for a larger number of cores than this one, right? So this is more specific about the node types that are at Kebnekaise, and here you can see that there are some number of cores in a node, and this is for a node where there are 28 cores, right, that are sharing the memory. So why is parallel programming needed? As if you want to scale your code, right, beyond some number of cores, as I mentioned previously, right? then you need some manner to make your code aware of all these resources. So here's the workflow in a cluster like HPC2N or UPPMAX, right? And here you can take advantage of all these computing nodes, right? If you know some protocol, right, to do this shared memory or distributed memory programming. So I include this picture here because once you start using the clusters, right, so you can underuse it, overuse it, or use it in an optimal manner. Yeah. So underusing the cluster, we mean that you request more resources than your program needs. So in some R scripts, you don't make use of many cores, right? And if you request more than that, then you can end up underusing the cluster. Also, you can overuse that if you set some number, some variable, right? So that enables the programming mode, and you over exceed or oversubscribe the number of cores that you allocated. So there are some tools in the centers, and especially this is available at HPC2N, right? It's called job usage that is available on the terminal. So you can type here job usage, and then the job ID, that is the number that you get when you use a sbatch command. This will give you a URL, and then you can monitor the job once it starts running. Unfortunately, this tool is not available on on most of the HPC clusters in Sweden, but there are some discussions to use it in a more general manner, right, on the clusters. However, in some centers, you can do an SSH to the computing nodes, and there you can use commands like top or htop to see if the resources that you allocated in your job are being used properly, right? Today, so we are talking about R, and I will talk about the some tools that are available in R for doing the threaded programming for shared memory architectures, and also for distributed memory, right? In threaded programming, there are some libraries for linear algebra, right, that are implicitly included in R. Yes, and you can make use of this threaded programming by setting an environment variable such as OMP num threads. Yes, so you don't need to do some coding, parallel coding in your R code, and you still can benefit from the parallelization because this is implicitly included in R. There are some libraries like LAPACK, BLAS, and others, right? And by setting this variable, then you can make use of the threads that are available on these libraries. So then you can check, first you can check if the libraries and packages that you are using have a threaded mechanism, yeah? And this is usually discussed in the documentation of the packages in R, right? And there is a key, most likely, where the developers set the number of threads or cores, right? For instance, uh, there is a package, yes, for making a cluster, right, in R. And here you can set some flags like allow parallel or the num threads so that you create some threads in the program. So for threading programming, there are several issues that need to be overcome by the coder. And one of them is data replication. And this is especially common in R, right? And when one uses some functions, yes, or some packages like do parallel, one can incur in some data duplication. And this happens because when one sets the number of workers, the workers needs to get a copy of the data. This is not uh, a difficult situation if the data that is replicated is not large. For instance, imagine that you have some number of megabytes in your uh, in your data, and then you set some number of threads. Then this will be replicated, this number of megabytes, right? Not a problem, but imagine that you have many gigabytes and you set several workers, then they will try to replicate this data and you can easily over exceed the memory available per node. Yeah. So this is an example. You can take a look at this for data replication and see how it looks like. In distributed memory, as I mentioned previously, one is not sharing the memory, but one is using some protocol to exchange data. Yes, and this is good for scalability. So Birgitte already mentioned a package that is available in R for doing this type of programming, and this is called RMPI. And something here that is not straightforward is that you need to know how to program in MPI, right? So if you know already MPI, then the language used in RMPI is very similar. However, we have noticed that this package is not that new and it hasn't been developed, yes, um, considerably, and therefore there are other options for doing MPI programming in R that can be more suitable for some clusters in Sweden, as Birgitte mentioned for Dardel. Yeah. So if you're dealing with big data, right, there are some options that you can use in R and that you can combine with the parallel programming. And for instance, you can use the arrow, right, for dealing with big arrays, also data table, big memory, and take advantage of these other programming models in parallel to get some workers doing the job in parallel mode. So I will spend more time on the following demo, right, which is uh, it contains the basic concepts of parallel programming. So this is a for loop, yes, in an agnostic language. So it contains four iterations, right? And here I am calling a wait function for 1 second. And here I am ending the for loop. So this wait function is just a manner to simulate something more complicated, right? So here you can put any other function that you want, but the point is that I want to simulate some workload, I would say. So if I run this in serial mode, yes, which means using one core or one CPU, yeah. So then the workflow will look like this one. I will wait 1 second for the first iteration, then 1 second for the next iteration, and so on until I reach the four iterations that I have here in this loop, right? So this is a serial mode for a serial code in R. So if you don't make any modification to your R code, right, and you don't include any parallelization function, then you will be using one core, right, and serial mode. But if we make the code aware of the number of cores, right, and we put some instructions, yes, to parallelize the code, we can do the following. We can execute the first function on one CPU, the second function, the second function on another CPU, and so on. And you can see here that the time will be divided by the number of workers. In this case, instead of having the time equal to 4 seconds, this will be divided by 4, yes, because we have 4 CPUs, and this will be potentially reduce the simulation time. Yeah. So how does this implementation look in R? So here I have a script called sleep.r. You can call it like this, or you can put a name to this. And in the wait function, I will simulate that with a sleep function in R. And for some number of times, it will be called, right? And in the modules, I will use these modules, yes. But notice here that I will be using the machine called Kebnekaise to run this script and to show you how it works. So I also will be using the do parallel package in R, which contains the main cluster function that will allow you to set a cluster and some number of workers, right? So here I define the number of iterations, and this part is what you will usually do with a serial function. So here you define a function with some parameters, right? And then here I have the for loop, and here I am executing this sleep function for 1 second, yeah? And notice here that, again, this function is just to simulate some workload, but here you can write any other code that you want, right? So then here I take the serial time, and I report the serial time, right? And here is the parallelization part, yeah? So here I start the function again, and notice here that this is the core part of the parallel program, right? Here I use the function called for each instead of a for, yes? And here I define the number of iterations from 1 to n. And notice here the key is that I'm using do par, yes? So for each also has a serial implementations, which is a do, yes? But if you want to use the function in parallel mode, then you need to use do par. And here is the workload that I want to execute. and in particular is the sleep function for 1 second. So then I start the cluster. I need to create a cluster with the function make cluster. And here I define the number of workers. Yeah. So in particular, because there are 4 iterations, I want to split it into 4. Then I use the value here that I store for n. Yeah? And then I need to register the cluster with this function. And here I take the time, yes, and report the time in this parallel time variable. So to run this code, yes, you can copy this, yes, and I already did it, and call it sleep.r, and then you paste that, yes. So then the script is there. I also need to load the modules, which I already did, like this one. And for running this job, yeah, you can write a script, as Brigitte mentioned. However, because this job is very short, right, and it doesn't require a lot of resources, I will use the command srun directly on the terminal, and here I will use the project that we have for this course. Here it is. This is the project that we have. And here I am requesting one task with a -n. This is one task. And here I am requesting the number of cores, -4. Yeah? Here I am specifying the time, 10 minutes. And I am using R script with the options no save and also no restore. I don't want to save the data. I don't want to restore the data. And this is the name of the script, sleep.r. So then I can submit it, and it will be sent to the queue. So run in this way will not run this program on the login node, but it will be sent to the compute nodes. So you can see here some reports from R, yes, when it tried to load the packages. And here you can see the lapse time. So in the serial mode, it was 4 seconds. And in parallel mode, it was around 1 second. So you can see that the time is not perfect. You will, I would say, never, yes, get the perfect speed up, which means you will never see exactly 1 here. And this is because there is some overhead, for instance, when you are loading libraries, copying the data, and so on. Yeah. And R also does several things behind the scenes when it is executing the functions. Yeah? So you will see some overhead here, and the speed up will not be perfect. Yeah? So here I provide you some exercises. So you can try this one, for instance. And the second one is more challenging, but it's also it's more advanced, yeah, but also it's more realistic. And this could be some bonus if you want to do that. You can try the first one, which is regarding the parallelization, yes, of a 2D integration algorithm. So here we know already the solution of this integral in 2 dimensions, which is 0, yeah? And here we will try to parallelize the summations, yeah? So these are the packages that you need to check if you have already installed, right? Parallel, do parallel. You can check first, and if you haven't installed that, then you can install it with the installed packages. So then you need to load the module for your R version. And in particular, I am using this one for HPC2N. So then we load the parallel and do parallel packages. And here you need to correct the number of workers in this fix me according to the instructions of the exercise. And this is the grid size that we are using for the integration. So how it works, here we define a function called integration 2D, which asks for the grid size, yes, this one, the number of processes, which are the workers that will be doing the job, and also the process index, which is the worker ID. Yeah? So here we need the interval size. And because we are integrating from 0 to pi, the interval size is pi divided by n. So then we define a cumulative variable called my sum, which starts from 0. And then we create a workload for each thread. And how do we do that? We need the grid size, the total number of beans that we will using, divided by the number of processes or workers. Yeah? So then here we create the beginning and the end for each worker, for the range that will be covered by each worker, right? And then here we start the integration, right, for each worker. Notice here that we need to define the beginning and the end, yes, because each worker has a different range, right? Finally, we compute and return the sum multiplied by the delta H, which is the bin size. Yeah. Also notice here that we are parallelizing only the x-axis. Yeah, the second axis is not parallelized. It is run on each thread in the same manner. So here we start the parallelization. We create a cluster as I did previously. Then we register the cluster. And then we use the for each function, yes, for the number of workers. And here we do the integration. So in the exercise, so you are asked to run this program for 1, 2, 4, and so on. Number of cores and threads here by fixing this variable. So then you can collect the timings in the job.out, yes, and then see what is the optimal number of cores that you need for your simulation. So then you can try this and let me know how it goes. So we have until 14:25 to do this exercise. So do you have any questions?